I'm going to send you guys an email this afternoon, evening, tomorrow. We talked a little bit about synthesis on a timed exam. Graded. You should have seen your corrected and graded syntheses on Canvas. There will not be a synthesis on your final. There will be a synthesis counted as part of the final exam school. So I'm going to email that to you. You will all have a different quality. So it's open note, it's open book. You can't go to Chem Center. If you guys talk to each other, if you guys just talk generally about stuff, that's fine. The take-home stuff is pretty hard. I've talked with some of you in office hours about this. Like, I in general like take-home work. Gives a little more time to be thoughtful and look at like we would actually do. If you were, if you're working as a chemist, that's what you would actually be doing. On the other hand, right, like when I give a take-home assignment, not just you guys, but I give any take-home assignment, I get sets of 7 or 8 that looks basically identical. So it's hard to include that as the final exam. So this will be a piece of your final exam. You'll have about 3 weeks, due December 7th, 2 o'clock. There will not be any extensions on it. 3 weeks is plenty of time. Like, probably, how long does it take you to write it all down? Like maybe 10, 20 minutes. The hard part is thinking about it, and working through that. So again, a synthesis, like every step has to work. I know people who give no partial credit on a synthesis. Because if if it's 7 steps and step 5 is completely impossible, won't give you any product, then that synthesis is wrong. I sympathize with that point of view, but as an introduction, I don't like it. But you should definitely stop and look at. I'll get a key up for the synthesis. I don't think I've put a key up for exam 2 yet, have I? Have not. Anyway, like get your synthesis, like treat it like writing a paper. Maybe don't, but college students typically don't treat writing papers the way I would imply. But you should, when you're writing a paper or a synthesis, like get a final version that you like and then set it aside for a couple of days and come back and look at it. And ask yourself, like, each step, does that work? Do you have like still a lot of people on the synthesis I graded are doing things like lithium aluminum hydride and H3O plus. When you mean 1 lithium aluminum hydride, 2 H3O plus. If you just mix lithium aluminum hydride and H3O plus, you get a 5. Right. So like pay attention to those details. It's a science class, and like on the one hand, details. Do you have to have all the details of everything memorized? No. But in the end, if you actually go to the lab to do stuff, the details are absolutely critical. So pay attention to that. You can talk to me about this assignment. I think there's anything. Anyway, I'm sure questions will come up about it. You can ask that. There may be a short, and by short, I mean 2-step or something, synthesis on exam 3. We'll see how that goes. Right. Questions so far? Yeah.
Is the final written for an hour?
Finals for 3 hours.
We haven't done any.
We'll see. It might be 3 hours. I haven't written the final yet. I haven't written exam 3 yet. Like I am. You guys have this. Look, you're the adult. I mean, you're all adults now, but the adults in your life are going to tell you how you should live your life, and you should listen to that. You'll get good advice. You should, do things well in advance. You should be prepared. You should pay attention to details. Don't imagine that most of the people in your life are doing. Most people are 10 minutes ahead of you. So, yes.
Oh,
No, sorry. We're not doing the ICL.
okay. No.
Yeah, fun. So when you tell Angela King that, take a picture of her face. I really probably should. I got my reasons. I'm not gonna tell you. Any other questions? So the final exam is a 3-hour block. I might well write a 3-hour final exam. Probably don't know. That's a long time. Any of you who get time and a half or whatever will get time and a half or whatever time limit I eventually put on it. So the final is at 2. I'm going to try to arrange for there to be one other alternate time. I don't guarantee that I will do that. Like I said, the synthesis problem, there will be no extension. It is like if you come and tell me, hey, I got a final like on the 6th, and then I got 2 on the 7th, like, yeah, that's finals week. So if you don't start your synthesis until the 5th, you're screwed. And you'll be screwed on whatever, how many points ever it is, yeah.
Just be good if that was synthesis could find besides like that one, like
Yeah.
work on it and the third, and there might be one courses.
It will be short. It will not be the 5-step. I like this. All right, another question. All right, I actually probably should know by now that when I look at a question I've written for an exam, oh, that's beautiful. Like that's probably not going to be a good like that's a hell of a question. The genius. All right, so we're talking about making amines. What do we get from this? Draw me a product. Under what conditions is this reaction good? Why is it base? What is base? What's another word to call a base? What does a base do? It's a nucleus. So base is an electron donor. So really you should think about bases and acids like Lewis acids and bases. We tend to think about them as Bronsted acid bases. And you know, again, most of the people in here, any chemistry you guys do later on is going to be in water. Like that's most of Earth-like. I don't know where I'm going with that sense. Most Earth-like work, whatever Earth-like work is with water. All right, so proton transfers in water are extremely important. The proton transfer from one water to another water, from hydroxide to water, or from water to hydroxide, hydronium. Anyway, this is an example of the SN2 reaction that you guys learned, like maybe the first reaction you learned after proton transfer are Lewis acid base reactions. So we've got a Lewis base. His carbon's partial positive, right? Bonded to a partial negative bromide. That CBr bond is polarized, bromine's electronegative. So we've got an electron donor attacking the partial positive carbon. Positive things, partial positive things are Lewis acids, electron acceptors. So really like 95% of what we do, maybe more in first year, you know, the first year of organic chemistry is Lewis acid based chemistry. So ammonia attacks the methyl carbon of methyl bromide. This will give us, draw what this gives us. We're going to break the carbon bromide bond. We're going to make a carbon nitrogen bond. And we get methyl ammonium bromide. That's actually the product. It'd be a white solid. So this, you may have seen this reaction if you've ever seen a demonstration with ammonia and hydrochloric acid. Like if I took an ammonia stream, so ammonia is a gas at room temperature. HCl is actually a gas at room temperature. We tend to encounter HCl dissolved in water, but dry HCl is a gas at room temperature. If I had like a hose, if I had a hose of ammonia and a hose of HCl, and I like just cross the vapor streams, you'd see a white precipitate in the air. That's ammonium chloride. So you can do the same thing. Methyl bromide's a gas at room temperature. We do that, we get methyl ammonium bromide to precipitate. In solution, this is not the final product. So what might happen next? The bromine does not take an H. So you guys should know from your recent acid base forays, right? Like an NH plus proton has a pKa of about 10, 9 to 11, say. So you want something to take that proton. Br minus doesn't do it, right? Br minus bromide is a pretty weak base. The conjugate acid of bromide is HBr. It's a very strong acid. So bromide's a weak base. The proton does get taken. What takes, in the whole mix on the board, what is the strongest base? Yeah, ammonia is the strongest base. And again, right, we don't have one of these and one of these and one of these. We have a whole bunch of these and a whole bunch of these. And then after the first reaction, at some point, for a very, very tiny amount of time, we do have one of those. Pretty quickly, we have a whole bunch of those. So the next step is actually for ammonia to take one of these, and this is pretty much an equilibrium that's very close to. Let me get this drawn up here, and then I'll talk about it. Right, so if ammonia takes the methyl ammonium proton, I get methylamine and ammonium chloride. And this equilibrium is going to be very close to 1 to 1 if we have equal amounts of material, right? I talked to some of you about the acid base assignment sheet. If you can judge where the equilibrium ought to lie based on pKa. Right, so you want the higher pKa. That's just an empirical measure of stability. So if one acid has a pKa of 12 and the other has a pKa of 4, we have empirically measured that the acid with a pKa of 12 is a weaker acid. So that would be favorable. If you don't have pKa's, and here you really don't, right? We've got methyl ammonium and ammonium. I've asked you guys to memorize 9 to 11 for both of those, right? It's possible one would be 9 and one would be 11 just based on that. They're not that far apart. But what you can do is you can look at the stability of the lone pair. So you can compare the stability of the two bases, which means the lone pair. So here we've got a lone pair localized on nitrogen. Here we've got a lone pair localized on nitrogen. The two sides are going to be roughly equally stable. They're not exactly equally stable, but they're close enough that you're going to have significant amounts of both. Okay, so if we run this reaction in ammonia as solvent, then we're going to have a lot more ammonia that would be coming in on this side, and that would push the equilibrium to the right. Okay, remember Le Chatelier's principle. If I disrupt an equilibrium by adding a reagent, the equilibrium will shift away from that reagent. If I pull a reagent out, reagent or a product out of the equilibrium will shift toward them. Right, so if I have more ammonia than methyl bromide, we'll push the equilibrium to the right. Okay, so all of this is by way of saying we can't really just make amines, right? Like if I wanted to synthesize methylamine, I can't really do it by just taking methyl bromide and ammonia, and I'm trying to explain why not. I've made methylamine now, but what happens next? What's the problem with this as a synthesis of methyl? It won't actually go, it might come back to here, but it won't go back to here. All right, so the carbon nitrogen sigma bond is way stronger than the carbon bromide sigma bond. So this reaction, the first step is essentially irreversible. So going backwards isn't the problem. So think about this logically. If going backwards isn't the problem, we're trying to stay in one spot, and going backwards isn't the problem. What's the problem with staying in one spot?
We go forward.
If we go forward, it's like you might not know what that means right now, but just like trying to solve that problem. If you resolve that going back can't happen, and I'm telling you we're not going to stay in one place, that means you must go forward. And the reason we go forward is, again, we have a lot of this, right? We have a lot of methyl bromide. So if I now have methyl bromide down here, that reaction, that's just going to react with nitrogen. Then this is also irreversible, sorry. And we get that, right? That nitrogen is an amine. It's a pretty good base, pretty strong base. It's also a decent nucleophile. So we can just do another SN2 reaction. What's the name of this compound right here? Not dimethylamine. Who said that? Dimethyl what? I can't hear you. Dimethyl ammonium, yes. Yeah, dude, just that. Dimethyl, two methyls on the nitrogen. I couldn't hear the end. I couldn't tell if you're saying ammonia or ammonium. So that's dimethyl ammonium bromide. All right, anyway, I'm sort of belaboring this at this point. The same thing can happen now. We have ammonia still in here. That can take this proton. We end up with this again is an equilibrium. We end up with NH4 plus. We get dimethylamine. This reacts with CH3 bromide. We lose the proton. We get trimethylamine. Same thing, we've got trimethylamine and ammonium, methyl bromide. Again, this is the step, I keep getting the steps. Now finally we're done. What's the name of this last one? What was it? Ammonium bromide. What ammonium bromide?
Tetramethyl.
Tetramethyl ammonium bromide. I fooled you by not writing CH3s. Okay, so the problem with this synthesis that I put up last time, right? The reason we can't, if I want to make methylamine here, I can't do that by I can't do that efficiently by taking ammonia and methyl bromide or methyl iodide or methyl chloride. Because it's going to over-alkylate. I'll wind up getting dimethylamine as well. I'll get trimethylamine. I might get some tetramethyl ammonium. Same thing if I wanted to make dimethylamine, it might stop at the methylamine. It might go on to trimethyl. Like there's no way to control this reaction well. And this is a part of any chemical process. We all, in class or in lab, we're always talking about yield. I think we're pretty careful to give you guys reactions that basically give one product really well. But for a lot of reactions where we just dump stuff together and it looks like a really good reaction. Basically, every reaction I've drawn on the board, every single step is a really good step. Like, oh, that will happen. That will be good. We form strong bonds. We do an acid-base reaction that's plausible. That doesn't mean it's a good reaction overall. If they're all good steps, we're probably going to get a little bit of all of it. Okay. So we want to exert a little bit more control over our amine synthesis, which is to say, if I ask you guys to make an amine, you should not use that. So here are some ways we could do this. So we could take draw the product of that reaction. And the Lewis structure of N3. So N3 is called the azide ion. 3 nitrogens all in a row, right? The nitrogen that we breathe, if I just say nitrogen, I either mean the element, probably I don't mean the element though, right? Most conversations you're going to have as a human, talking about nitrogen, will be referring to N2 gas in the atmosphere. All right, N2 gas, I think I said this last time, is super inert. Right? We can make it react, but it's hard. And you can tell it's inert because it makes up 80% of air and it doesn't do anything, right? Like oxygen's constantly being broken down and then reformulated up in the upper atmosphere. Carbon dioxide and water come and go, right? Even as global carbon dioxide concentrations in the air are going up, if you guys have ever read those graphs closely, right, there's always some seasonal variation. There'll be a tick down, there'll be a tick up. It's higher. We measure that. You might know where carbon dioxide is measured, like officially.
Like in high schools.
You can do it from ice cores, and this is one of the problems with communicating like climate. Is it's a science, and there are some like wild error bars on things, right? There's never been a measurement ever that didn't have some error in it. And so if I count how many people are in this room, there's not going to be an error. Right? There's a no number we can pinpoint. But doing stuff like CO2 in ice cores, which is how we figure out like how much carbon dioxide was in the atmosphere 10 million years ago. Like, that's got some pretty big error bars. Today we measure it. The official measurement is in places like Mauna Kea, 15,000 feet in Hawaii. Hawaii is like one of the most remote places on the planet in terms of being far away from industry. Because if you think about here, right, like in Winston, where is there a lot of carbon dioxide? Going to be a lot of carbon dioxide sort of over roads, stuff like that. Where there's not as much. Go to the woods where the trees are taking it in, right? So like it will vary. Same thing with water vapor. There's more water vapor over a lake than there is over my backyard. So anyway, my mind's it's Monday. My mind is straight. Azide is 3 N's together, which is not super stable. It's a good nucleophile. It's as poisonous as cyanide.
In the same way. So cyanide, if you reviewed cyanide as a poison, it binds the iron and hemoglobin irreversibly, right? So our hemoglobin, the iron in that molecule binds O2 weakly and then carries it where it needs to go, but the O2 can come off because the bond between the iron and the oxygen is very weak. Azide and cyanide, really good small sort of O2 sized molecules that are strong bases, bind the iron and just stick to it. So azide is, you don't want to, if you're using azide, you don't want to drink it, eat it, you know, get it inside you. The other thing azide does is it bound to things that can be an explosive. Right, so explosives tend to be molecules that will liberate gases exothermically. So they'll generate energy. The generation of that energy will accelerate the reaction, right? So I've got a whole bunch of molecules here that are going to decompose. If they start to decompose, right, as you heat reactions up, they go faster. So a really exothermic decomposition will produce heat. That'll make the molecules around it react faster. There are lots of reactions that exothermic. We call this, and you guys have reflux things now. So imagine you reflux something and you get what's called an exotherm. The reaction just like violently generates every little bit of heat. Every time two molecules react, it generates heat, then the molecules around them accelerate, that generates more heat. Generally what happens though is it just boils the solvent and it shoots out the top of your reflux condenser. So if you ever come visit my hood, there's very likely going to be stains just above where you would put reflux condenser. It's like I will have exotherm stuff. An explosion happens when that exotherm generates gas products that give you pressure. And so N3 can break down to release N2. So most explosives that we have release nitrogen, either N2 or NO molecules, nitrogen oxides, water, and CO2. Those are the common gases that get released. So, you know, humans have gotten very good at chemical engineering. So we build molecules, like some tiny little molecule that'll release like 8 gas molecules. Exothermic. Those are the good explosives. I'm not supposed to teach you how to make explosives. They're against that. So, azide, if you draw this Lewis structure, it's going to be a line, right? Turns out they're actually, you got some double bonds there. Quaternary nitrogen is going to have a positive. If you work through the charges and the number of electrons, you're going to have one excess electron. So in the resonance structure I've drawn there, you guys might have seen this when you did resonance structures in Gen Chem. So 2 double bonds, that'll give you 2 negative nitrogens on the ends and a positive nitrogen in the middle. It's kind of is analogous with ozone. And then you can draw a resonance structure where you can move one of these double bonds to be a triple bond, have a 2- out at the end. You can't get away from the central nitrogen being positive. So the overall shape of this ion is linear, which makes it a really good nucleophile, right? So if you think about cyanide being a good nucleophile, because it's bullet shaped, the electrons, the nucleophilic electrons are directly like in line with the 2 atoms. There's essentially no steric N3. N3 has the same sort of thing going. So this reaction is going to be N3-, doing an SN2 reaction. Giving us methyl azide. I'm not going to ask you how to name azides. And then sodium bromide would be the other, if you care about inorganic molecules at all. All right, methyl azide is a really dangerous compound to make. From a safety point of view, if you have azide, if you have nitrogen-nitrogen bonds or oxygen-oxygen bonds, the general rule of thumb, and this is not gravity or anything, this is really is a rule of thumb, but the general rule of thumb is if you have a nitrogen-oxygen bond, if you have fewer than 5 heavy atoms, meaning non-hydrogens, for nitrogen-oxygen, oxygen-oxygen, or nitrogen-nitrogen, you've got a molecule that can explode. So methyl azide, decent, if you make that and isolate it, it can explode. Metal azides also, like iron, chromium azides, really good explosives. Why might I want to make that compound? Even though it's explosive and toxic. So if I want to make methylamine, right, and my problem over here with using ammonia and methyl bromide, I get my methylamine, but then it keeps reacting. At this point, if we draw this Lewis structure out, it can't keep reacting. Bless you. Right, so methyl azide is done. It's not nearly as nucleophilic as azide itself. So then the second thing I can do here is I can reduce this somehow. You guys remember the symbol for reduction. I'll get into gas, right? Into gas goes away. It's a really stable molecule, nice energy sink, and I'll get an amine. And so at this point, what I can do before I do the reduction right? I can separate the methyl bromide. So when I get my methylamine, there's no more electrophiling. Right? The whole problem over here is I generate methylamine in the presence of an electrophile. So over here, I make my methyl azide, I get rid of the methyl bromide, then I reduce it. So how might we reduce it? Some of this is a review. What's a good reducing agent? Got some ideas here. Hydrogen, platinum, lithium aluminum hydride. I mean, let's just kill it. Why don't? What else? The second one ought to lead you to. There we go. Those are the ones you know about. Turns out triphenyl phosphine will do it. Tin chloride will do it. There's actually a lot of ways to do this. But those top three ways you guys all said definitely reduce an azide to an amine. Hydrogen gas, that's usually a little cumbersome to do. Hydrogen gas is awkward to work with. Lithium aluminum hydride certainly will reduce an azide, but it's overkill. Sodium borohydride does the same thing. Again, I think I talked about this back at that point. Not that this is likely to come up, but if you guys are ever offered a choice between lithium aluminum hydride and sodium borohydride, and they both work, choose borohydride. You can have water around, you can have protein solvents around, you can just weigh it out, you can leave it sitting out, it's not going to burst into flames or anything. Lithium aluminum hydride will catch on fire just if it's annoying. So try to use this. All right. The other way that's in the book to do this, and I'm using methyl bromide here. It's an SN2 reaction. You can make any amine you like via an SN2 reaction with azide and reducing the azide afterwards, right? So this could be a decyl group, it could be a benzyl group, like it doesn't have to be methyl, it could be anything. The other, this is quite a bit older. This is called the Gabriel synthesis, and I feel obliged to put this on here. So you can take this nitrogen anion. So this is a thal imide, right? We've got a negative nitrogen that's sitting between two carbonyls, right? So that an NH here would be quite acidic, being between two carbonyls. And then if you draw the resonance structure here, right? If you draw this resonance structure, you can make an aromatic ring. You get some aromaticity in the ring on that 5-membered ring. So this is a really surprisingly stable anion. We take this reaction, we do an SN2. We get this. So now we've alkylated that nitrogen. And again, the point here is at that at that point, that nitrogen is done, right? That nitrogen can't react further. So all these methods that we're going to see to to make amines that aren't just taking an amine or ammonia and an alkyl halide are meant to get away from the problem presented in this first panel, where if I take an amine and I react it with an alkyl halide, it can just react and react and react. Right, at this point, this is not a nucleophilic molecule, right? So it's going to stop, I can separate it, I can isolate this compound, and then I'm going to get rid of the reducing agents here. Let's leave NABH4 here. This is probably what I would use. But again, if you need to make that azide, if you need to reduce the azide with a carbonyl around, you wouldn't choose NABH4. You'd choose hydrogen. If you need to reduce the azide and there's an alkene in the molecule, you choose NABH4, right? You're trying to pick a reagent that only reacts with the azide. Here on this dilimide, now you can't, we could reduce this, all right? So lithium aluminum hydride would work. What happens if I use lithium aluminum hydride on this molecule? Right, it reduces the carbonyls first to alcohols, but remember there's now like a leaving group on it. Like what I would get would be that's a bond on a Nike swoosh. Right, so if I use lithium aluminum hydride and then I protonate, I'll reduce those carbonyls all the way to alcohols, and I'll liberate the amine. I can also hydrolyze. And I'm not going to go into this. Very often in this hydrolysis step, they add hydrazine, which is in rocket fuel, which is fun. The hydrazine can actually be a nucleophile and attack the two carbonyls, but you'll wind up with the amine, and then either so if you just hydrolyze, we'll get right the dicarboxylic acid anions, or we get this weird looking molecule. The Gabriel synthesis was a huge advance. Like making amines is very, very important. Okay, I've talked about amino acids. You guys are going to take biochemistry. Maybe you've already had cell, and you're going to see a lot of amino acids. Making biologically relevant molecules means you need to be able to make amines. So starting even before we really properly understood biochemistry or a lot of organic chemistry, people were trying to synthesize amines. Azide kind of came later. The Gabriel synthesis was really the first good way to make an amine from a nitrogen-containing compound, where that nitrogen was going to only react one time and go in one place. It is not so used today, so I'm not going to talk about it really more than I already have. I just want to emphasize the syntheses on the board so far. The whole point is you have a nitrogen that will react one and only one time. Right, same thing here. So azide, there's one nitrogen that will react. Dilimide, there's one nitrogen that will react. And then the reaction stops. You can get rid of the reagent that's going to react too many, overreact, and then isolate the amine. Essentially, these kind of are like pre-protected nitrogens. You want to think about it like a protecting. Okay, think about your lab experience this year. Right? Everybody wants to think about their lab experience. What way would you suggest to make an amine? Based on your lab experience.
be a long standoff. Yeah.
Probably. Decided.
No, not your, sorry, you misunderstood. Yeah, that would be my guess too, but I'm not giving 200 undergraduates sodium base. Of the last you've done, what have you done that would make him? What have you done that made him? Look at my senses right.
Do they use sometimes?
Did those make him? Those started as a meeting. You're in the ballpark. Finish the word. Yeah, reductive amination. That like where you made it a mean. At least one of you's read one of your lab reports. I never read my lab report either. I should admit that on tape tonight. All right. So yeah, reductive amination is really how we do this today. All right, amination, as the word implies, we aminate things. And it involves a reduction. So I don't remember what the, can I come up with it? Probably not. I mean, I'm teaching this stupid class and I can't. Something like that, right? It's got too many carbons. That? Let's go with that. I hope you guys smell that vanilla, the vanilla. Really nice smell. Draw the product you get out of this. You should always smell the compounds in lab. We've gotten civilized, and so we no longer taste the compounds in labs. That's a big loss. Definitely taste. You should definitely smell them. Yeah, draw what you get out of it. So in all seriousness, right, you should not smell the compound, all the compounds. When compounds have a name like vanilla, wintergreen, smell the wintergreen. Amines, on the other hand, don't smell the amines. We have humans have evolved a pretty nasty reaction to the smell of amines. Talk about that in a minute. All right, so we have an aldehyde, we have an amine. We're going to make from this an imine, I-M-I-N-E. So we're going to lose water here. And actually, we didn't have to do anything special in this reaction to make this reaction go. And the reason is, well, let me ask you. Why did we not have to do anything particularly special to make this reaction go? What's interesting about the product that favored the product here? Had something to do with color as well. Yeah, so you've got an aromatic system conjugated to another aromatic system via this carbon-nitrogen bond. That also gave the really nice color. If you think back to that lab, so you mix these two compounds up. I think this was one we did, as a solid. We ground it up, color formed, and then so that's the formation of the imine. And then the next step was sodium borohydride. And again, we just did this in one pot, right? You made the amine and then you just dumped in the sodium borohydride. And I think I can't remember if we had methanol or not. You had normally here, I can't remember offhand what you had in lab. Normally here, you would have a protic solvent of some sort. And this reduces the carbon-nitrogen bond, double bond, just like it would reduce the carbon and oxygen double bond. And there's your amine. So reductive, this is the reductive amination process. In reductive amination, we first make an imine, we make a carbon nitrogen multiple bond. Sometimes you're gonna have to drive this. Like if the amine was not an aryl amine, or the aldehyde or ketone was not an aryl aldehyde or ketone, we would probably have to force this reaction a little bit. And by forcing it, we could heat it up and sort of boil the water away, or we could put a drying agent in. Like you can do a whole lot of things to force this reaction. If you wind up with a highly conjugated imine like this, you usually don't have to. So reductive amination is going to be two steps. We're going to make an imine, we're going to make an imine from either an aldehyde and an amine or a ketone and an amine. And then you reduce the imine. Sodium, we can use sodium borohydride. We could also use lithium aluminum hydride. Right, so remember, again, some of this is for review. Sodium borohydride is the weaker of the hydride reductants. So it reduces aldehydes and ketones. It'll reduce amines. It will not reduce carboxylic acid derivatives other than like an acid chloride. So you tend to want to use the weakest reagent you can. And I mean, I was kind of making some jokes about this. Somebody said lithium aluminum hydride, like, kill it. Like you don't want to use that really strong reagent because, like, one is you know probably it's more expensive, which is true. You could have a fire, but the bigger worry is, let's assume you're a professional and you're funded. So you're not going to have a fire and you can afford the reagent. Using a more powerful reducing agent means there's other functional groups than you want could get reduced. So you kind of want to be as gentle with your molecule as possible, right? If I could get this reaction to go without screaming at the molecules, I want that to happen. Okay, so like I said, imine and then reduce. So let's see if you guys can draw the product of this. All right, so I'm going to jump into this. I've thrown a bit of a wrinkle in here by having this be a secondary amine. So again, nomenclature of amines. A primary amine is has a nitrogen with one alkyl group on it or one carbon group on it. Secondary has two, tertiary has three. A quaternary amine is going to have to be an ammonium. And you'll hear those. So my wife works, I don't remember what all I probably said way too much about my wife in here. She works for a company that makes coatings, paints and coatings. It's like, we paint the walls. They used to let you put lead in there. You guys have all heard about it. This is fascinating, both chemistry and sociology. They used to put lead in the paint. Anybody know why they did that? There are a couple of reasons. One is you get much better color. The vibrancy is much better. The second reason is it keeps bacteria from growing on it. Pretty good, right? You don't want bacteria growing on your walls. What does that say about the lead? It's toxic, yeah. If it kills bacteria, it probably kills you. We get away with that with antibiotics by either designing the molecule to selectively kill bacteria, or just, it's a dose thing, right? And there's a lot of medicine for which this is true, that we're trying to kill something in us that there's not much of, so we can get away with that. Again, whole other fascinating topic. Anyway, we stopped using linen. So they have to put things in the paint that will keep the bacteria down, keep the mold and bacteria down without killing us. And what they landed on were quaternary ammonium salts. And so it's basically soap, right? A quaternary ammonium salt has a nitrogen that's got 4 bonds to it on one end, and then a long hydrocarbon chain. So it can insert into bacterial cell walls and stuff. So primary amines have one alkyl thing is going to be a NH2 in equilibrium with an NH3 plus. Secondary amines are like this one. That nitrogen's got 2 alkyl things on it in equilibrium with an NH2 plus. Tertiary amine would have not an H, no H there, right? It would just be a nitrogen and 3 alkyl things be in equilibrium with an NH plus. And a quaternary amine is going to be a nitrogen with 4 carbons on it that can't be protein. So I threw the wrinkle in here is you should draw as a product of step 1. That's right. Like this would be the product of step 1. Right? If I gave you this on exam 2, that's what I would hope you would draw. And so then you might reasonably ask me, like, well, what's the sodium borohydride going to do? Before I talk about the sodium borohydride, what could you convert this molecule to the amine, to an amine? Let me ask you this. Busy talking about paint. What do you need to do for this reaction? Right. This is now an alkene. So if you can make an enamine, you can just hydrogenate it. Should also be a reductive amination. Right. So we could just take this hydrogen, platinum, palladium, rhodium, whatever, do that. It's a really nice way of doing this. I mentioned making amines for biomolecules. Most biomolecules are chiral. We've worked out a lot of really nice ways to hydrogenate enamines like this. Right, this now is going to be a chiral molecule. That nitrogen can be forward or back. Get a pair of enantiomers. If the hydrogen comes from the front, that nitrogen goes back. The hydrogen comes from the back. The nitrogen comes front. And we have catalysts that will selectively make one or the other. All right, the sodium borohydride, then you might ask, like, what are you talking about? You can't. Sodium borohydride should not react here. But what happens in methanol is this winds up with a little bit of H plus. And now the borohydride will reduce this. These are chemical mechanisms. If you dissolve an enamine into a protic solvent, you'll have a very, very tiny amount of aminium. Right? So this equilibrium highly favors the enamine, but you'll have a little bit of aminium cation on it. That can be reduced. When that's reduced, right? It's reduced. That's an irreversible thing. Reducing that step is irreversible. Reducing that aminium is irreversible. That's what I'm trying to say. All right. I'm going to do this in the center because this is the nicest way to do this. It involves
I think I'll, actually, tell you what, let me just draw the reaction and then I'll talk about it the rest of the time, so. All right, so you can do reductive amination in one pot, and you can do this using a reagent called sodium cyanoborohydride. While I write the reaction up, I want you guys to draw a Lewis structure for the cyanoborohydride ion, right? The CnBH3 anion. And then you can write that reaction down if you want. All right, so sodium cyanoborohydride, the Na is going to be like all the Na you ever see in a molecule. It's going to be +1. Going to ignore that, right? It makes an ionic bond. Doesn't form anything. The central atom for the cyanoborohydride is boron. 3 hydrides, and then a nitrile. And that whole thing has a negative charge. All right, the formal charge, if you go into this, formal charge resides on the boron. Right, we did this with borohydride way back. This has been long enough ago that I know you guys remember sodium borohydride reduces things, but think about why it does that. Okay, so borohydride, you would have a 4th hydrogen here, a formal negative on the boron, but the negative charge would actually reside out on the H's. So those H's would react as if they're H minus. Where is most of the negative charge in this molecule? It's on the carbon, right? So cyanide, you guys should recognize cyanide. Cyanide by itself is a decently stable anion. And it's electronegative. And so borohydride, I should draw that in here, right? What I was saying. And borohydride, the molecule distributes a full negative charge over 4 hydrogens equally. Each of those hydrogens is equally negative. In cyanoborohydride, most of that negative charge is on the cyanide, with just a little bit left for the H's. So do you think that would make those H's more or less nucleophilic? It'd be less, right? They have less, the H is more neutral. A neutral H is not going to be nucleophilic. So sodium cyanoborohydride is a weaker reducing agent than even borohydride. So borohydride is a more powerful reducing agent than cyanoborohydride. And what that means is cyanoborohydride is usually not powerful enough to reduce a ketone. Right? So if I just have this ketone that on the screen, not get that on the screen. Sorry. All right, so if I take cyclohexanone, any ketone or aldehyde, pH 4.5-ish, sodium cyanoborohydride does not reduce it. If I lower the pH to 1, the cyanoborohydride does reduce the ketone. So what happened? Why can cyanoborohydride reduce a ketone at pH 1 and it can't do it at pH 4.5? Question you should ask is, basically what we know here is cyanoborohydride can't reduce a ketone. So that means it's got to reduce something else. What's the other thing that it would reduce? What might happen to a ketone if you put it in strong acid? pH 1 is strong acid, right? Where would it protein? On the O. Was that an O, like an exclamation?
No.
O?
I'm not.
Oxygen. All right, good. Right, so at pH 1, and pH, any pH really, you're going to have this equilibrium. But the protonated ketone is going to be a much more important player in the equilibrium at pH 1 than it is at pH 4 or 5. And now the cyanoborohydride can attack the protonated, right? By protonating the ketone, we make the ketone more electrophilic. So a weaker reducing agent, a weaker nucleophile can add to it. This is basically just what you guys saw all through chapter 19 and 20, right? If you have a carbonyl compound, you add acid to it, weaker nucleophiles can add to the protonated carbonate. So at pH 1, we protonate the ketone and it reacts. So then what does that suggest is being reduced in the reaction at pH 4.5? Draw out what you think, not a mechanism necessarily, but draw out the steps of this reaction. Draw out the steps of this reaction. What's the first intermediate in amine formation? Actually, that's probably not. First intermediate is not what I'm thinking. If you go through this whole mechanism, right? So nitrogen is going to attack the carbonyl. We're going to move some protons around. We're going to end up with a tetrahedral intermediate. I'm just going to draw
sorry, I guess I should just draw one of these. And then this will kick out, well, this will kick out water. And we'll get this aminium cation. That is what gets reduced. The aminium cation is what gets reduced. Right, the aminium cation looks like a protonated ketone. It's not quite as electrophilic because the nitrogen's more basic. But this is the one where the H minus adds in there. And there you go. So the genius of this method, well, I shouldn't have circled that. The genius of this method is controlling the pH. All right, and if you actually ever need to do this in a lab, you probably will have to play with the pH a little bit. Might be that you need it to be 5, you might need it to be 4. You need the rate of addition to be fast enough to make the aminium cation, and you need the aminium cation to hang around long enough. Right, so if we take the pH too high, we don't form enough aminium cation. That H gets taken off, right? The NH plus gets taken off too fast. If you take the pH too low, you reduce the ketone and you protonate the nitrogen, right? These amines are strong bases, so if you're under too acidic conditions, then you wind up not having enough nucleophiles. So generally speaking, between pH 4 and 5, you can find conditions where the aminium cation forms and it gets reduced. Yeah. So this is not 3 steps. This is just you mix all this together. So that's at pH 4.5, pH 4 to 5. You can mix the ketone or aldehyde, the amine, and the sodium cyanoborohydride, and the only thing in there that can form and get reduced is the aminium cation. You end up with amine. This one can actually have, like, we're mixing all this up at the same time. So depending on the various rates, this can have the same problem we encounter with just using an amine and a methylbromide. But again, by adjusting concentration, you can usually play with this and make it what you want. If you can't, the safest way would be, well, like you could make an azide, but you can't make a secondary amine that way, right? You could use dilimine, but you can't make a secondary amine that way. You could if there were going to be a couple of things on here, you just make the amine, isolate the amine, and then reduce it with borohydride. That's a much safer way to know you're only going to get monoalkylation of the nitrogen. You lose it in this step, right? So you lose. So nitrogen adds in. Like we actually go through the. We got 5 minutes left. I'll go through. Let's go through it. Looking at you all, it looks like that has confused you. So. I think I didn't do this. I feel pretty confident now I did not do this. Right? When we did chapter 19, I didn't do this mechanism, and I talked to some of you in office hours. Nucleophilic attack on a carbonyl. If it's a weak nucleophile, it's got to be protonated. Strong nucleophiles can just attack. Acidic conditions, you don't want. When the nitrogen, remember I said acidic conditions, you want everything protonated, basic conditions, you want everything deprotonated. With the nitrogen, it's somewhere in between. The nitrogen is a pretty strong base, but then when it attacks, it's going to be protonated. Okay, so then this will be a solvent-assisted proton transfer. One of the NH you're worried about gets transferred to the O- at this point. All right, and then this is not, again, we're at pH 4.5, so you can protonate. This can kind of go 2 different ways. We can just kick out hydroxide, or we could, let me use the orange jet today, so we'll protonate it. Right, this O grabs a proton off water. At pH 4.5, this is probably what's going to happen. Then we kick water out. That gets us our aminium, which then gets reduced. So like I said, when you're making an imine, for the mechanism for an imine, the protonation states are difficult to work out. So on the one hand, that's confusing for you guys. On the other hand, unless I've been really clear that it's pH 1 or pH 14 or something, it's okay to have a quaternary protonated nitrogen alongside a strong base O minus, right? Because again, equilibrium wise, this O minus is a stronger base than the amine to start, but not by so much, right? The pKa of the protonated amine would be 11, pKa of the alcohol would be 16. So the difference in stability there is only 5 orders of magnitude, so which is usually enough to establish an equilibrium. And again, for all these reactions, if you can establish an equilibrium and put an irreversible step at the end, then the reaction goes. Like this equilibrium may favor starting materials 1 million, 10 million, 1 billion times. But I get to here, and then it gets to there, and this may be 1 million times, and then this may be 1 million times. This is infinity that way. Right? So basically here, this is like, you know, when you spill water on your kitchen counter. And it's very, like the water kind of runs all over until it gets to the edge and it goes on. So it can sort of go anywhere on the counter and then on. So this last step where we add an H minus into the aminium gets us to the amine, and that's it. I think, yeah.
Wait, what happened to the
Oh, I'm just, it stays there. I want, yeah. So I wanted to make this point. I saw this on a couple of syntheses, and I think there was a question on the exam maybe. Right, if you look at all these steps, we're making a bond between the nitrogen and the carbonyl carbon. We're making nitrogen carbonyl carbon bonds. Nothing ever happens. Sorry, should have. Nothing ever happens at the chiral carbon. So don't change the stereochemistry of the chiral carbon. So when you have an SN2 reaction, hopefully you guys have kind of internalized inversion of configuration for an SN2. That inversion of configuration only happens at the carbon that gets attacked. So if you have a chiral center not getting attacked, it just stays the same. Thanks for bringing that up. I put that intentionally there. It probably, like, so actually, no, this is not a chiral atom, sorry. Yeah, sorry. No. All right, 74 minutes is my limit. How did you guys like the azo dyes? We will talk just a little bit about azo dyes on Wednesday. I'm gonna put up a couple of problems from chapter 21, just finish a few more alpha carbon stuff. Next week on Monday, we're going to talk about polymers a little bit. You guys are doing, hear me out for like 30 more seconds. This week you're doing a polymer lab that's really cool. And so be patient with it. Some of this is to my students, but this is kind of to everybody. The chemistry itself is really easy. Like you dump stuff in a vial and you shake it. The rest of the lab, read through it before you come to class because the rest of the lab involves some engineering and playing around with it. But it's pretty cool. I think it's pretty cool. So, all right, I'll see you. I'm going to be around out here for a few minutes. Give me like 10, 15 minutes to get stuff. I'll be on.
That's next week, class. Take a long time. Or
Next week's? No.
Sorry.
I was say, there is no lab next week.